All right, welcome to the Explainer. Today, we're diving into one of the most famous charts in all of science. I mean, think about it. It's this single page that organizes the fundamental building blocks of, well, everything you've ever touched, seen, or been. You know, when you look around, the universe is just unbelievably complex, right? From the stars burning millions of miles away to the smartphone right in your hand. So the first step to really understanding any of it is to find the order hiding underneath it all, to find the rules that govern the chaos.
And that's where this chart comes in. The periodic table. It's not just some boring list of elements. No way! It's the map. It's the pattern for the building blocks of reality itself.
So how in the world did we get this incredible cheat sheet for chemistry? How did we go from just a random mess of different substances to this beautiful, elegant, and predictive masterpiece? Well, a lot of the credit goes to Dmitry Mendeleev. He started arranging elements by their atomic mass, but here was his stroke of genius. He left gaps. He predicted that elements we hadn't even found yet would go there, and he was right. But the real breakthrough, the moment it all clicked, came from Henry Moseley. He realized the secret wasn't the mass, it was the number of protons. Once he rearranged the table by that, everything just snapped perfectly into place. Okay, so let's get into it, because the real magic of the table is how it's set up. It's all about this logical grid system. Every single element has a specific address, and that address is determined by what's going on inside the atom. Okay, so first you've got the horizontal rows. There are 7 of them, and they're called periods. The easiest way to think about these, they just tell you how many shells or layers of electrons an atom has. So if an element is in period 3, boom, it's got 3 electron shells. Simple as that. Then you have the vertical columns. These are the groups, and you should really think of them as families. Seriously, elements in the same group, they act alike. Why? Because they all have the same number of electrons in their outermost shell. And that's the key, because chemical reactions, it's all about those outer electrons. And this is where you can really see it in action. It's so cool. Take a look at lithium. Its electron arrangement is 2, 1. So 2 shells means it's in period 2. 1 electron in that outer shell puts it in group 1. Now check out aluminum. 2, 8, 3. 3 shells puts it in period 3. 3 outer electrons and it lands in group 13. See, its address on the table is literally spelled out by its electrons. All right, so now that we get the layout of the neighborhood, let's go meet some of the residents. By looking at the different groups, we can explore these unique elemental families and their very distinct chemical personalities. So let's head all the way over to the far right side, to group 18. These are the noble gases. You can think of them as the cool kids of the periodic table. Their outer electron shells are completely full, which is basically the dream for any atom. They've got everything they need, so they're super stable, totally content. They just don't react with anything. And being so chill and unreactive actually makes them super useful. We use helium in balloons because it's light and, won't burst into flames. The bright glow of an advertising sign? Yep, that's the noble gas neon. Argon gets used in light bulbs to keep the filament from burning out. And even radion, which is radioactive, can be used to treat cancer. Okay, so now let's jump all the way over to the other side of the table to group 1, and you'll see the complete opposite. These are the alkali metals, and they're everything the noble gases aren't. They've got just one single lonely electron in their outer shell, and they are absolutely desperate to get rid of it so they can be stable like the noble gases. And this is the key thing to remember. That overwhelming need to give away one electron defines their whole personality. It's what makes them such soft metals. And it's what makes them so incredibly extremely reactive. Okay, so we've seen that going down a column is like visiting a family where everyone has a similar personality. But what happens if we take a road trip across a row? Well, that tells a whole different story. It reveals a clear, predictable pattern. Let's take a little walk across period 3. We start on the far left with strong metals like sodium and magnesium. When they react with oxygen, they form what are called basic oxides. Just think of them as the opposite of acids. As we keep moving right, we end up with nonmetals like sulfur and chlorine. They form acidic oxides, which, you guessed it, create acids in water. It's this smooth, predictable shift from one character type to another. And smack dab in the middle of this journey, bridging that gap between the metals and the nonmetals, you find silicon. It's a semi-metal, or a metalloid, meaning it's got a foot in both worlds. It has properties of both. And that special place, that a little bit of this, a little bit of that property, that is exactly why silicon is the absolute heart of our modern digital world.
Its ability to be a semiconductor, to sometimes conduct electricity and sometimes not, is the foundation of every single microchip in our computers and phones.
Okay, for our last stop, let's turn our attention to that huge block of elements right in the middle of the table. This is kind of like the powerhouse of the whole operation.
These are the transition metals. Now, remember those super soft alkali metals we talked about? Well, these guys are the opposite. They are what you probably think of when you hear the word metal. They're hard, they're dense, and they have really high melting points. There's a reason we build bridges out of iron, not sodium. I mean, their physical properties are impressive for sure, but the real superpowers, they're all chemical. These metals act as catalysts, speeding up crucial industrial reactions. They form these brilliantly colored compounds. We're talking the reason paint and stained glass have their amazing colors. And they're versatile, able to exist in different forms, which makes them key players in all sorts of chemical reactions.
And that right there is the real magic of the whole thing. The periodic table is so much more than a poster on a classroom wall. It's a predictive engine. If you know where an element lives on the table, you can understand how it's going to act. It reveals the beautiful, hidden logic that runs our entire universe.
And you know, this story isn't even finished. Scientists right now are creating new, super heavy elements, adding to that bottom row. And it makes you wonder, right? It leaves us with this awesome, thrilling question. What new properties, what new families, and what new secrets of the universe are we just about to unlock?